everyone, I am Jeshel Sinches and my report is all about traffic flow and queuing theory. So the analysis of vehicle traffic provides the basis for measuring the operating performance highways. In undertaking such an analysis, the various dimensions of traffic such as number of vehicles per unit time, flow, vehicle times, vehicle speeds, and the variation in traffic flow over time must be addressed because they all influence highway design and highway operations, both of which impact the importance or the performance of the highway. Table of contents. 1 is the traffic stream parameters, 2 traffic flow, speed and density, 3 basic traffic stream models, 4 models of traffic flow, 5 is the queuing theory and traffic flow analysis, and 6 is the traffic analysis HW bottlenecks. First is the traffic stream parameters. So traffic stream parameters can be characterized by a number of different operational performance measures. A traffic stream that operates free from the influence of such traffic control devices as signals and stop signs is classified as uninterrupted flow. This type of traffic flow is influenced primarily by roadway characteristics and the interactions of the vehicles in the traffic stream. 2 is the traffic flow speed and density. Traffic flow speed and density are values that form the underpinnings of traffic analysis. Traffic flow is defined as Q is equal to N over T, where Q is traffic flow in vehicles per unit time and N, number of vehicles passing some designated roadway point during time, and T is the duration of time interval. Traffic flow speed and density. The time headway is between the passage of the front bumpers of successive vehicles at some designated highway point. The time headway is related to T as defined. T is equal to N summation I is equal to 1 then H sub I, where T, duration of time interval, H sub I, time headway of the I vehicle, the elapsed time between the arrivals of vehicles I and I minus 1, and N, number of measured vehicle time headways at some designated roadway point.
Good day everyone, let us proceed to our next topic, which is all about basic traffic stream models. Traffic stream models attempt to establish a better relationship between the traffic parameters. It is essential to understand the interaction of the individual microscopic measures in order to fully analyze the operational performance of the traffic stream. Speed density model. So the most intuitive starting point for the developing a consistent, generalized traffic model is to focus on the relationship between speed and density. The section of highway with only one single vehicle on it, so the density of that in vehicle per minute will be very low, and the driver will be able to travel freely at the speed close to the design speed of the highway. So this speed is referred to as the free flow speed because vehicle speed is not inhibited by the presences of other vehicles. As more and more vehicles begin to use a section of highway, the traffic density will increase and the average operating speed of vehicles will be declined from the free flow value as the driver slow to allow for the maneuvers of other vehicles. Eventually, the highway section becomes congested, leading to a jam density. So the density is determined by vehicle length and driver space, with the jam density being the highest density condition. This occurs when traffic stops. U is equal to 0. The possible representation of the process described is the linear relationship. As you can see in the screen, or as you can see in the picture, so there is an illustration of a typical linear speed density relationship. So this relationship can be expressed as U is equal to U sub F, the quantity of 1 minus K over K sub J. Then, or where U is a space mean speed in mile per hour, UF is equal to the free flow speed in miles per hour, K is the density in vehicles per miles, and KJ is for jam density in vehicles per mile. So the overall speed density relationship is better represented by the three relationships. 1. A linear relationship at a low density that has speed slowly declining from the free flow value. Number 2. A linear relationship over the large medium density region. Number 3. A non-linear relationship near the jam density as the speed asymptotically approaches zero with increasing density. It is the number of vehicles occupying a unit length of the lane of the roadway at a given instant. It is expressed in vehicles per kilometer or VEH per hour. Using the assumption of a linear speed density relationship, parabolic flow density model can be, as you can see in the screen or as you can see in the picture, we have different formulas there in order for us to substitute, in order for us to obtain the general formula. So Q is equal to UK and U is equal to U sub F, the quantity of 1 minus K over K sub J. Then we can obtain a formula of Q is equal to U sub F, the quantity of K minus K to the power of 2 over K sub J. The maximum flow rate, Q cap, represents the highest rate of traffic flow that the highway is capable of handling. This is referred to the traffic flow at the capacity or simply the capacity of the roadway. The traffic density that corresponds to this capacity flow rate is K cap and the corresponding speed is U cap. Equation for Q, CA and K cap and U cap can be derived from differentiating Q is equal to U sub F, the quantity of K minus K to the power of 2 over K sub J. So as you can see in the screen, we have the maximum flow and the free flow speed UF, which is not equal to 0. So after we substitute these formulas, we can obtain the general formula of Q cap is equal to U cap multiplied by K cap, or Q cap is equal to U sub F times K sub J over 4. Returning to the linear density model, a corresponding speed flow model can be developed by rearranging U is equal to U sub F, the quantity of 1 minus K divided by K sub J, to K is equal to K sub J, the quantity of 1 minus U divided by U sub F. And by substituting these two formula, we can obtain the general formula, which is U is equal to U sub J, the quantity of U minus U to the power of 2 over U sub F. So let us proceed to our next topic, which is about models of traffic flow. So traffic flow speed and density are related, but attention now shifts to a more microscopic view of traffic flow. This involves modeling the time between successive vehicle arrivals, known as vehicle headway. Models for non-uniform flow assume vehicle arrival patterns are random processes requiring selecting a probability distribution that accurately represents observed traffic arrival patterns. An example of such a distribution in the Poisson distribution, which is expressed as that P times N is equal to the lambda times the time to the power of N multiplied by E to the power of negative lambda times time over N factorial, where P times N is the probability of having N vehicles arrive in time P, lambda is the average vehicle flow or arrival rate in vehicles per unit time, T is for the duration of the time interval over which vehicles are counted, and E base of the natural logarithm, which has a value of 2.718. So as we can see, we have an example of a Poisson model. An observer counts 360 vehicles per hour at a specific highway location, assuming that the arrival of vehicles at this highway location is Poisson's distributed. Estimate the probabilities of having 0, 1, 2, 3, 4, and 5 or more vehicles arriving over a 20-second time interval. So the solution, the average arrival rate, lambda, is 360 vehicles per hour or 0.1 vehicles per second. Or using this in equation 5.23, with P is equal to 20 seconds, the probabilities of having exactly 0, 1, 2, 3, and 4 vehicles arrive are, using the formula earlier, so when n is equal to 0, P times n is equal to, our value sa lambda is 0.1 times the atom time, which is 20, to the power of n, which is 0, multiplied by P to the power of negative lambda, which is 0.1 times time 20 over 0 factorial. So we can come up to an answer of 0.135. When n is equal to 1, so P times n is equal to, value na to sa lambda, which is 0.1 still, times 20 to the power of 1 times E to the power of negative lambda, which is negative 0.1 times 20 over 1 factorial. So it is equal to 0.271. So when n is equal to 2, P times n is equal to 0.1 times 20 to the power of 2 times E to the power of negative lambda, which is 0.1 times the time, which is 20 over 2 factorial. Then we have an answer of 0.271. When n is equal to 3, P times 3 is equal to 0.1 times 20 raised to the power of 3 times P raised to the power of negative 0.1 times 20 over 3 factorial is equal to 0.180. Thus, when n is equal to 4, it is equal to 0. P times 4 is equal to 0.1 times 20 to the power of 4 times E raised to the power of negative 0.1 times 20 over 4 factorial. It is equal to 0.090. For 5 or more vehicles, P times n, which is less than or equal to 5, is equal to 1 minus P times n, which is greater than 5. It is equal to 1 minus 0.135 minus 0.271 minus 0.271 minus 0.180 minus 0.090. It is equal to 0.053. A histogram of these probabilities is shown in this figure. As you can see in the screen, the number of vehicles arriving in a 20-second time interval probabilities in parenthetic.
So, good day everyone. I am Nhicole Sumalpong and I will be discussing about queuing theory and traffic flow analysis. So, what is queuing theory or queuing model? It is the study of how queues form, how they function, and why they malfunction. Queuing theory examines every component of waiting in line, including the arrival process, service process, number of servers, number of system places, and the number of customers. So, bali mo ni siya ang laing term of pagpila. Pila sa ATM machine, pagpila sa bisag asa nga lugar nga naay kapilahan, pwede sa pagdawat pug ayuda. What is traffic flow analysis? So it is a study of interactions between travelers and infrastructure. It seeks to describe in a precise mathematical way the interaction among vehicles, drivers, and the infrastructure. The infrastructure consists of the highway system and all its operational elements, including control devices, signage, and markings. So, unsa ang significant nilang duha? Nganong ma-relate man silang duha? So, the formation of traffic queues during congested period is a source of considerable delay and results in a loss of highway performance. Under extreme conditions, queuing delay can account for 90% or more of a motorist's total trip travel time. As is well known, the problem of queuing is not unique to traffic analysis. So, bali, ang pagpila or ang linya sa mga sakyanan is usap po sa causes, mga traffic, and the engineers or the experts are here to analyze the traffic flow kung pila ba ka or pila ang oras sa delay, pila ba ang mga vehicles during at that time. Bale, example, na sa traffic for 1 hour na ay 240 nga gakulumpong or galinya-linya nga mga sakyanan. So next is the dimension of queuing models. So the sole purpose of traffic queuing models is to provide a means to estimate important measures of highway performance, including vehicle delay and traffic queue lengths. Example for this is the required length of left turn base and the number of lanes at intersection. Dimension of queuing models, dire na mabase or dire na magkuha ang o pila ka vehicles ang madelay. So next is queuing models are derived from underlying assumptions regarding arrival patterns, departure characteristics, and queue disciplines. Lambda or the average vehicle arrival rate. Two possible distribution of the time between the arrival of successive vehicles were considered. First, the equal time intervals derived from the assumption of uniform deterministic arrivals. Then secondly, exponentially distributed time intervals derived from the assumption of Poisson distributed arrivals. So, in addition to vehicle arrival assumption, the derivation of traffic queuing models requires assumption relating to vehicle departure characteristics. Of particular interest is the distribution of the amount of time it takes a vehicle to depart. For example, the time to pass through an intersection at the beginning of a green signal, or the time a driver takes before deciding to proceed after stopping at a stop sign. As was the case for arrival patterns, given an average vehicle departure rate denoted as mu in vehicles per unit time, the assumption of the deterministic or exponential distribution of the departure times is appropriate. Example is the time to pass through an intersection at the beginning of a green signal, or the time a driver takes before deciding to proceed after stopping at a stop sign. So dili man pud nato jud makuan nga magdungan jud ng example naka sa stoplight, nag-stop ka sa stoplight. Then pagkahiman-himan, syempre napakay kasunod ka sakyanan. Ikaw example naka sa car, then ikaw driver. Dili pud nga matik na dayon nga dungan pud mo nga mag-start. Example, ikaw may kinaunhan sa linya, so dapat ikaw may nakabalo nga, stop, nag-go signal na, nagpa-under na ka, usa po po, magsunod-sunod ng mga nakasunod nimo. Important aspects of queuing models. It is the number of available departure channels. For most traffic application, only one departure channel will exist, such as a highway lane or group of lanes passing through an intersection. However, multiple departure channels are encountered in some traffic applications, such as at toll booths, on turnpikes, and at entrances to bridges. So, kasagaran jud ay ang atoang departure channel or mga gawsanan or exit way nato is mostly isa ra joy available. So we'll discuss about two queuing discipline. So kinaunhang discipline is first in, first out, or FIFO, indicating that the first vehicle to arrive is the first to depart. So unsay may mga example ani. So the example for this is example naka sa drive-thru. Diba sa drive-thru maglinya man jud mong mga naisakyanan, then og kinsay unang nakasulod or kinsay unang gi-approach sa server, may unang makagawas pod og unang makakuha sa ilahang pagkaon. Then the second is last in, first out, or LIFO, indicating that the last vehicle to arrive is the first to depart. Example pod is the kanang na pictures nimo sa gallery. Di ba ang imong mga pictures dito sa 2018 naa pa sa pinakala sa imong page sa imong gallery. Example na po na siya sa last in, first out. The next is queuing models, or it is identified by 3 alphanumeric values. The first value is the arrival rate assumption. The second value gives the departure rate assumption. Then the third value indicates the number of departure channels. So next is traffic arrival and departure assumption. D is for deterministic distribution and the M is exponential distribution. D/D/1 queuing model, it is the deterministic arrival, departure with one departure channel. Then M/D/1 queuing model, it is ang M exponentially distributed arrival times, then deterministic departure times, and one departure channel. So D/D/1 queuing. The case of deterministic arrivals and departures with one departure channel, D/D/1 queue is an excellent starting point in understanding queuing models because of its simplicity. Sa cover sa ako ang report is ang ako lang matakal or mahatagag example with the solution is D/D/1. Ang motakil na about sa M/D/1 is my other group mate. Example for D/D/1 queuing with constant arrival and departure rates. So, vehicles arrive at an entrance to a recreational park. There is a single gate at which all vehicles must stop, where a park attendant distributes a free brochure. The park opens at 8 a.m., at which time vehicles begin to arrive at a rate of 480 vehicles per hour. After 20 minutes, the arrival flow rate declines to 120 vehicles per hour, and it continues at that level for the remainder of the day. If the time required to distribute the brochure is 15 seconds, and assuming D/D/1 queuing, describe the operational characteristics of the queue. So, the solution. First is we begin by putting arrival and departure rates into common units of vehicles per minute. So, lambda is equals to 480 vehicles per hour over 60 minutes per hour is equals to 8 vehicles per minute. For time is less than or equal 20 minutes. Then the second is lambda is equals to 120 vehicles per hour over 60 minutes per hour is equals to 2 vehicles per minute for time is greater than 20 minutes. Mu is equals to 60 seconds per minute is over 15 seconds per vehicles. X is equals to 4 vehicles per minute for all t or for all the time. So, equation for the total number of vehicles that have arrived and departed up to a specified time t can now be written. Define t as the number of minutes after the start of the queuing process. In this case, the number of minutes after 8 a.m. The total number of vehicle arrivals at time t is equals to 8t So, equals to 80 for t less than 20 minutes. So, and 160 plus 2 times t minus 20 for t is greater than 20 minutes. So, similarly, the number of vehicle departures is 40 for all the time. The preceding equations can be illustrated graphically as shown in the figures. When the arrival curve is above the departure curve, a Q condition exists. The point at which the arrival curve meets the departure curve is the moment when the Q dissipates. No more Q exists. In this example, the point of Q dissipation can be determined graphically by inspection or analytically by equating appropriate arrival and departure equation, that is 160 plus 2 times t minus 20 is equals to 40. Solving for t gives t is equals to 60 minutes. One 60 plus 2 times alpha x minus 20. Alpha x kay pangitaon man ang t, which is 60 minutes. So the time is, or the for t is equals to 60 minutes. Thus, the Q that began to form at 8 a.m. will dissipate 60 minutes later, 9 a.m., at which time 240 vehicles na ang nilabay o na abot, and are for 4 vehicles per minute times 60 minutes. Another aspect of interest is individual vehicle delay under the assumption of a FIFO queuing discipline. The delay of an individual vehicle is given by the horizontal distance between arrival and departure curves starting from the time of the vehicle's arrival in the queue. So by inspection, the 116th vehicle to arrive will have the longest delay, 20 minutes, and vehicles arriving after the 239 vehicle will encounter new queue delay because the queue will have dissipated and the departure rate will continue to exceed the arrival rate. So bale, ang ika 160 nga sakyanan kay naay pinakadugay nga delay sa tanang mga ni-arrive og nihawa sa recreational park. So it follows that with the LIFO, or the last in first out queuing discipline, the first vehicle to arrive would have to wait until the entire queue clears, 60 minutes of delay. So, kinsa pa'y kinaunang naabot mo pa'y dugay kay makagawas, or dugay kayo ang delay para makagawas siya, which is 60 minutes of delay. The total length of the queue at a specified time expressed as the number of vehicles is given by the vertical distance between arrival and departure curves at that time. For example, at 10 minutes after the start of the queuing process, or bale, nagsugod man sa 8 a.m. So, after 10 minutes, so bali 8:10 a.m. The queue is 40 vehicles long. So, 40 na ang naglinya para maka-intra sa recreational park. And the longest vertical distance between arrival and departure curves will occur at the time 20 minutes and is 80 vehicles long na. So, kung 8:20 na, nadungag agi muragi times 2 ang kadaghanan sa vehicles. Total vehicle delay defined as the summation of the delays for the individual vehicles is given by the total area between the arrival and the departure curves, and in this case is in units of vehicle minutes. In this example, the area between the arrival and the departure curves can be determined by summing triangular areas, giving total delay dt as dt is equals to 1/2 times 80 times 20 plus 1/2 pa jud sa 80 times 40, which is the total of 2,400 vehicles per minute. Finally, because 240 vehicles encounter queuing delay as previously determined, the average delay per vehicle is 10 minutes, or 2,400 vehicles per minute, or 240 vehicles. And the average queue length is 40 vehicles, or 2,400 vehicles per minute for over 60 minutes. So, mag-review ta. So, what is the total time of delay by all vehicles? So, nakuha na ang D sub T is equals to 1/2 times 80 times 20 plus 1/2 pa jud sa 80 times 40. So, mag-total siya sa 2,400 vehicles per minute. What is the average delay per vehicle? 2,400 vehicles per minute. I-overrun pa dyan siya sa 240 vehicles for 10 minutes per vehicle. Average kani siya, average queue length. So, what is the average queue length per vehicle? So, 2,400 vehicle per minute over 60 minutes is equals to 40 vehicles. So, that will be the end of my discussion. Thank you.
So, good morning everyone. So, I am Al-amhira as Tapsin. So, I am the last supporter for the group B. So, first, I will discuss the MD1 queuing. MD1 queuing. So, MD1 queuing, the assumption of exponentially distributed times between the arrivals of successive vehicles or the Poisson's arrivals will, in some cases, give a more realistic representation of traffic flow than the assumption of uniformly distributed arrival times. So, we have this formula, traffic intensity. So, traffic intensity is equals to the average arrival rate in vehicle per unit time over the average departure rate in vehicle per unit time. So, for example, we have the problem. Consider the entrance of the recreational park described in example 5.7. However, let the average arrival rate be 180. So, not a 180 vehicle per hour. And Poisson distributed exponential times between the arrivals over the entire period from park opening time 8 a.m. until closing at dusk. compute the average length of the queue, average waiting time in the queue, and the average time spent in the system. So first, we will solve for the traffic intensity. So kanina ang formula. So naatay 180 vehicles per hour. Pero as stated dito sa example 5.7, naaputo siya given na sa isa, ang interval sa isa ka vehicle is like 15 minutes. So, one vehicle, like 15 seconds, I mean. So, kani siya, ato siyang i-convert sa into minutes. So, 180 vehicle per hour times 1 hour over 60 is equals to 3. 3 vehicles per minute. So, ang kaning 1 vehicle per 15 seconds, so i-convert ko na ito siya o vehicle per minutes para same na siya pa. So, we have 1 VE over 15 seconds times 60 seconds over 1 minute. So, we have 4 vehicles per minute. So, nanatay, ano siya, atong ginatawag ang average arrival rate according sa problem. Then kanin siya, mo siyang average departure. So using these two values, makakompute na ito sa internal at sa traffic intensity. So P is equals to 3 VE per minute over 4 VE per minute. So we have 0.75. So, muna na siya atong traffic intensity. So, ang gipangutanan na sunod is ang average length of the queuing vehicles. So, natin formula diri. Traffic intensity squared over 2 times 1 minus traffic intensity. So, Q is equals to P squared over 1 by 2. Times 1 minus P. So, nanataan ni, which is 0.75 squared over 2 times 1 minus 0.75. So, we have 1.125. So, mana siyang atong average length of queuing vehicles. So, yung ipalita is ang average waiting time in the queue. So, sa average waiting time, napatay yung formula. Traffic intensity over 2 times average departure rate times 1 minus ang traffic intensity. So, pag mangita naman siya sa W is equals to equal siya sa 0.625 minutes per vehicle. So, wala siya sa MD1 queuing. So, proceed ka sa ikalawa, which is ang MM1 queuing. MM1 queuing. So same problem. Ang sa MM1 queuing, di ba natin ito eh? Four or three. B is 0.75. So therefore, ang formula sa average length of the queuing vehicle is ngayon po siya, Q is equals to P squared over 1 minus traffic density. Then, ang sa yung average waiting time, kanina po yung formula. And then, sa yung average time spent in the system is 1 over average departure minus ang yung average arrival rate. Kanina po siya nga formula. So, using the MM1Q, same problem. Ang value sa atong average length of the queue is equals to 0.75 squared over 1 minus 0.75 is equals to 2.25 VE. Vehicle. For this one foot is, di ba ang value natin is 4. Ano na ba dito? Baliktad. Anyway, 4 na rin. So this one is 3 over 4 times 4 minus 3. So we have 0.75 minutes per vehicle. Sunod din, the average time spent is equals to 1 over 4 minus 3, which is equals to 1 minute per vehicle. Next na na.
Ikat-kat na lang.
So next na itong queuing is ang MMN. Queuing. So, bridge application. So at the entrance, kani siya example. Sige, dito na ako mag-example. So, a more general formulation of the MM1 queue is the MMN queue, where N is the total number of departure channels. MMN queuing is a reasonable assumption at toll booths, on turnpikes, and at the toll bridges, where there is no up to more than one departure channel available, more than one toll booth open. So, natin given yung formula, which is E equals to 1 all over summation and C factorial. Another formula. This one is for N. Less than or greater than N. So, in this formula, nagpapad. So, PO is the probability of having no vehicles in the probability of having no vehicle. the system, where ang PN is the probability of having n vehicles in the system, where ang PN is greater than n is the probability of waiting in the queue. Probability of waiting in a queue. So the small letter n stands for the number of vehicles in system, and the big letter N stands for the number of departure channels. N sub C, this one stands for the departure channel number, and the B is the traffic intensity. So for the average length, nahikot ang yung formula. Napod siya PO, which is the probability of having no vehicle times the traffic intensity, number of departure channel plus 1 over number of departure channel factorial times and 1 over 1 minus traffic intensity over squared. Then for the average waiting time, traffic intensity times ang kanang value rate over Q minus 1 over departure rate. So for the average time spent, we have traffic intensity plus average length all over arrival rate. So for example, so nasa igual. Example, so a convenience store has 4 available parking spaces. The owner predicts that the duration of customer shopping, the time that a customer vehicles will occupy a parking space, is exponentially distributed with a mean of 6 minutes. The owner knows that in the busiest hour, customer arrivals are exponentially distributed with a mean arrival rate of 20 customers per hour. What is the probability that a customer will not find an open parking space? So putting mean arrival and departure rates in common units gives you departure rate is equals to 10 vehicles per hour. And ang arrival rate is like 20 vehicles per hour. And so, namakay niya na. So, ang yung value sa P is equal to 2 vehicles. And because of P over N, so ang yung P over N is 0.5, which is less than 1. So, less than 1 man siya. So, ang gamitan ng mga equation is the probability of having this equation. Nanakaan yung values. So, paano din ka? Ang ipangitap dito sa problem is ang probability of the customer will not find an open parking. So, ano yung formula? So, PO is equals to 1 over 1 factorial 2 squared 2 factorial plus 2 So, 4 na siya taman kay 4 naman ka available spaces ang given sa problem. So, kaning 0.5, igani siya sa P over N, ay traffic intensity, I mean. So, natin traffic intensity nga 2, then ang N nato ani, ang big letter N, which is ang number of departure channel is 4. So, 2 divided by 4, we have 0.5. So, na siya 0.5. So, ano PO, i-calculate na ito kapag 0.1304. So thus the probability of not finding open space upon arrival is so ang probability ano niya, kaya diba ang values na yung n is greater sa big letter n, so kaya diba kaya tayo 6 man to, so ang 6 is greater than 4. May 4 man ang kan. So, ano siya nga formula na malimong subaon? Ang P n plus 1 over n factorial n1. Ayan siya P ang traffic intensity. P over n. So, we have 0.1304 times 2 the power of 5 over 4 factorial times 4 and 0.5. So, ang answer na dahil sa iyo pa is 0.087. So, mga na siya sa MMN.